Hi everyone! Today we're going to talk about geology on other planets in our solar system. So we're going to look at Mars specifically, look at a little bit about its geologic past, and then we're also going to explore the geology of some moons in our solar system that are interesting, including our own. So as a quick recap, we can talk about sedimentary rock, sedimentary structures, and formations on Earth. And spoilers, they're not exclusive to the Earth. So what we learned about sedimentary formations can help us piece together the history of other planets and moons as well. For example, if you see a whole bunch of mud cracks, that probably tells you there was water present and the water was pretty stagnant. It eventually dried up, producing mud cracks. If you have ripple marks, that can tell you a lot of information. Again, it's probably going to tell you there was water present, and in some sense it was going back and forth. If you have asymmetric ripple marks, that means the water was going steadily in one direction. If you have symmetric ripple marks, it means the water was going back and forth pretty evenly. You can also have organism track marks. This is something so far we've only seen on Earth. Boo would like to say hi. Hi. So far, we've only seen organism track marks on Earth. Any sort of trace fossils or real fossils have only been found on Earth. However, there's the distinct possibility that they could be found in other places as well. Here's an interesting feature. This is an example of an alluvial fan. This is an alluvial fan on Earth where we have a river traveling towards a wide open expanse. The river empties out into this flat area and the sediment gets deposited. Bigger sediment close to the opening of the river, smaller sediment further on. And so the structure is called an alluvial fan. Do these images look similar? Notice how we have a river opening up onto a flat area, sediment gets deposited, and we have this nice fan shape. Here's another one. River opening up onto a flat area, sediment gets deposited, and we've got this nice fan shape. Here's another interesting one. A big crater, but look what's happening at this corner right here. We have this beautiful fan shape in this corner of the crater, indicating that there was some water that emptied out into this flat space at the bottom, producing an alluvial fan. By the way, these pictures are from Mars. So what does this tell you? This tells you that in the past, Mars had water. It had flowing water, and the water opened up into flat expanses, like the bottoms of craters. Here's another example from Earth. This one is an example of a delta. You've got a river opening up into a pretty calm, larger body of water. Sediment gets deposited, and you get this built-up formation called a delta. Here's some more pictures that may look familiar. On the left, you have a picture from Mars. On the right, you have a picture from Earth. Again, you can see very, very similar features appearing. Here's another example. This one, again, is from Mars. Very similar features to deltas that you'll find on Earth. What does this tell you? That liquid water from a river emptied out into a larger, calmer basin, just like an ocean or a sea, and that happened on Mars. So, were there ancient oceans and seas on Mars? Absolutely. And evidence is starting to point more and more to that fact. Here's an artist's interpretation. This is just an artist's interpretation of what it may have looked like on Mars, maybe 1 billion or so years ago. Now we're going to talk about some features on Mars that point to the fact that Mars probably used to have a significant amount of liquid water on its surface in its past. The first example we're going to look at is this interesting feature. This is where I mispronounce all the words. This is called Naneti Vallis. So this is a valley that was carved out by water on Mars. Here's a zoomed in picture of the same valley. The next example from Mars is called Hellas Planitia. This is a giant crater in the southern part of Mars. And what's interesting is if we zoom into this crater, we can see some really interesting features. Right now I'm using Google Maps. I don't know if you knew this, but Google Maps can allow you to zoom into features on all kinds of planets and moons in our solar system. So I highly recommend you have a look at Google Maps space and click on some of the interesting moons and planets that you can zoom in on. Right now I'm on Mars. As you can see, I've got Olympus Mons right here, which is the largest volcano in our solar system. If we go to the bottom of our image, you see this giant basin. This is a huge impact crater, and that's actually Hellas Planitia. I'm going to zoom in. If we look at this crater, around the slopes of the crater, what does this look like? Kind of like we have an ancient river carving big gouges in the rock all the way down to this opening at the bottom, depositing what looks like sediment in the formation of a delta. We have another valley here, probably carved out by liquid water over the ages, forming this nice big delta. Wonder what that looked like billions of years ago. Other evidence of ancient water on Mars come to us through some Mars rovers who have uncovered a lot more evidence that water was very plentiful in the past. For example, they've sampled sedimentary rocks, looked at their composition, looked at their shape, and looked at the structures that they formed on the surface of Mars. Here's an interesting article you may have seen from recently. There is still flowing water on Mars, except it's in the form of a very, very, very salty brine. Here's a nice image from NASA. See these dark colored streaks? Those are salty, salty, salty water that's flowing up and down the slopes of certain regions of Mars' surface, and the length of the stripes depends on the temperature at that particular season. Curiosity has taken some really interesting image of Mars' surface and also sampled some interesting stuff on Mars' surface. Here's a really interesting picture from Curiosity. This is a sedimentary rock that was once part of an ancient riverbed. Now they can tell it's sedimentary rock based on its composition. They can also look at some of the features. For example, in this image, the sediments that make up this rock are actually quite large, too large to be transported by wind alone. Therefore, they must have been pushed along by water. The other interesting thing is the sediments themselves are rounded. They've been weathered as they've been pushed along the bottom of this river or stream. Here's another example of water existing on Mars in the past. This is an image from the surface of Mars that actually shows some cross-bedding, which means sediment was deposited by some sort of a medium, in this case it was water, that was flowing in one direction, producing cross-bedding. The type of rock that formed this cross-bedding is actually shale. Shale is a type of mudstone, and mud requires water. Now, can you think of any other flowing liquids that could exist in our solar system? We know that they existed in the past on Mars, most likely. The Cassini-Huygens probe used radar to map rivers on Titan. Rivers on Titan aren't made of liquid water, they're made of hydrocarbons, liquid hydrocarbons like methane and ethane. One thing they've noticed when they map the surface of Titan is that weathering and erosion is quite different than it exists on Earth, and that's because it's a totally different liquid that's doing the weathering. Hydrocarbon streams are actually cutting through water ice mineral. Here's an interesting image from NASA. This is a zoomed in image of some of the dunes that exist on Titan. Just like dunes in our desert, which are made of sand, which is mostly made of quartz, on Titan, the dunes are actually made of hydrocarbon sand. And as you can see, comparing pictures on the left to pictures on the right, the dunes are actually very similar looking to the dunes from Earth. Now, Titan has a very interesting series of liquid hydrocarbon lakes and rivers. In this image, we can start by zooming in at the top. The dark areas are the liquid hydrocarbon lakes. The whiter areas are the rock or the solid surface of Titan. And as we scroll down, you can see some features that are very similar to features on Earth. We've got some rivers or streams that are cutting into the rock and snaking out just like rivers and streams on Earth. In this image of Titan, you can see a lot of dunes, a lot of close-ups of the dunes of Titan. And again, if you compare this with images of dunes from Earth, they look very similar, except of course the particles, the sediments that make the dunes, are composed of very different materials. Titan has a lot of features. It's a fairly big moon. It also has mountainous regions. Here's a zoomed in image of some mountainous regions on Titan. Here's another interesting image from the surface of Titan. This one was taken several years apart by the Cassini-Huygens probe. The dark areas represent the hydrocarbon lakes. The light areas represent the solid surface. Notice the scale. This distance right here is equal to 20 kilometers on the surface of Titan. Notice how there are some very interesting, which look like solid features that are missing from one year to the next. What could that be? Nobody knows. If something has no or very few impact craters in our solar system, what does that tell you about that surface? Everything in our solar system was bombarded by lots of impacts over their history, so that's telling us that something must have weathered them. And therefore, the ground is pretty new. One really interesting example in our solar system of something with a high turnover rate is Enceladus. And if we were to zoom in on the surface of Enceladus, we would see very few craters. What you're seeing here is just ice. Very few craters, because all of this ice has a high turnover rate. Here's another zoomed in image of the surface of Enceladus. This could very easily be a picture of a glacier taken on Earth, and you wouldn't know the difference. This is what Enceladus looks like zoomed out. So even on a large scale, craters seem to be clustered a little bit more at the poles. Here's an image of the cratered parts of Enceladus, which are on the northern and southern poles. One thing that you can see is some of the cracks are cross-cutting the craters, telling you the cracks came later, the craters came first. And here's a full stretched out map of Enceladus. We can zoom in on some cratered regions at the north. As we get closer to the equator, we get fewer and fewer craters. So younger and younger surface. Remember, underneath this ice, there's likely a thick layer of liquid water. The moon is a really great example of preserving impact craters from the history of the solar system because there's nothing to weather it away. The moon has some really clear regions of light versus dark, and these are typically called highlands and lowlands. Based on this image right here, and based on the idea that younger surfaces of a planet are ones with fewer impact craters, which regions, highlands or lowlands, look like they're the oldest? Well, if you're looking at impact craters, there's a much greater density in the lighter regions, which are the highlands. And yes, those are the oldest ones. The moon has no atmosphere, no plate tectonics, and no history of water. So the rocks on the moon are entirely igneous. The highlands contain intrusive igneous rocks, very high in plagioclase feldspar, which is the white feldspar, so it has a high albedo. It's very shiny and reflective. The lowlands contain extrusive, mafic igneous rocks, mostly basalt, which makes them dark and makes them have a low albedo. Let's go back to Google Moon and see what we can see. One of the interesting things about Google Moon is that they actually tell you where the Apollo landings were. We're going to zoom into Apollo 15 because Apollo 15 looked at a really interesting feature on the moon, and that was a rill. So if I go to visible and I zoom in a little bit further, you can see this feature right here. It almost looks like a stream or a channel, but it's not because the moon never had rushing water. What this is actually a tunnel created by the collapse of a magma tube. And Apollo 15 actually investigated this region. So they took samples and they took images from this area. One interesting thing you can do on Google Moon is zoom right in, click on some of these different locations, and you can see pictures of exactly what they did on that mission. Speaking of preserving craters from our solar system's early formation, Mercury is a great example of that. Mercury is another planet with no atmosphere. Here we are back on Google Maps space, and now we're looking at Mercury's surface. Look at all of those craters, one overlapping the other. One thing I'll do is I'll zoom in to a whole bunch that have overlapped, and I'll show you a cool trick on dating craters. If you see a whole bunch of craters that are overlapped, you can always tell which ones are oldest and youngest, based on which ones are overlaid. So you can see this crater in the background. Not only is it covered by a whole bunch of other craters, the edges are also not very well formed, which is telling you it's the oldest one in this picture. This crater, where the edges are also not very well formed, overlaps or cross cuts this one, telling you this big one is the oldest in this picture. The ones that are newest are the ones that don't have any craters cross-cutting them. And you can see the edges of the newest craters are very clean. The next interesting object in our solar system that we're going to look at is Pluto, which we only learned about very, very recently when New Horizons went to Pluto to take some interesting pictures. I'm back on Google Maps right now, and now we're looking at the surface of Pluto. Pluto has a lot of really different features on it. However, it's mostly composed of nitrogen ice, with some carbon monoxide, but mostly nitrogen ice. The most prominent feature on Pluto is, of course, the heart shape here. This heart shape is made up of nitrogen ice, and it's split into these interesting cellular shapes. It's bordered by a whole bunch of mountains. And as you go to certain parts of Pluto, you'll see more and more craters telling you this surface is quite a bit older than Sputnik Planitia, which is this region here. There are no craters, which tells you this has a very, very high turnover rate. It's likely that this region here, the heart shape, Sputnik Planitia, is made up of a whole bunch of convective cells of nitrogen ice. Scientists are still trying to understand exactly how that works. Here are some interesting features that have been photographed on the surface of Pluto. The first one I'm going to show you is an interesting feature which could be an ancient lake of nitrogen ice on the surface of Pluto. So here's an interesting image of Sputnik Planum or Sputnik Planitia, where you can clearly see the cellular shapes made up of nitrogen ice. If we zoom in, you can even see that these cellular shapes have very distinct borders, and on these borders are little clusters. These clusters could be water ice. Not far from this region are a whole bunch of rugged uplands. So we have a lot of different geology happening on one little dwarf planet that we only learned about very recently. The other interesting feature of Pluto is that it has a lot of water ice as well. Here's an image that shows you the water ice concentration on various parts of Pluto. One of the interesting things you can notice is it tends to be concentrated in the older regions, almost the mountainous regions. Why that is, nobody's really sure yet. And finally, just to show you some of the variety of landscapes on Pluto, here's a high-definition image that shows you a close-up of Sputnik Planum on the right, going through some interesting highlands and mountainous regions, and you can start to see some craters happening on the left. So here's Sputnik Planum. Notice that when you get up close, there's some really interesting texture going on as well on these nitrogen ice cells. That borders onto a mountainous region where we have more and more water ice content. Remember, this is rock hard water ice because we're in the farthest reaches of our solar system. And as we get over here, we can start to see some craters telling you the ground is becoming a little bit older, less turnover. So I encourage you to go online, go onto Google Maps, space, and explore some of the parts of our solar system.